Hello and welcome. I want to thank y'all again for joining me again. In today's video, I wanted to go over the essentials of trig. Trigonometry is really just the study of right triangles. So you're going to be seeing a lot of right triangles inside of this unit, or rather chapter, I suppose, but you'll understand that these transcendental functions are incredibly important for our understanding of the world around us going forward. Trig is very applicable in the real world, so even if you're not watching this for calculus, this still serves a purpose rather than just wanting to know the derivative of sine or the integral of tangent. But I digress. To start out, I wanted to first define what is the angle that we're going to be working in. And the thing about degrees is they aren't really plottable, or they don't really work. So we actually have a way of converting this. Well, a circle, that's an ellipse. A circle, that is still an ellipse. A circle. And let's say that we have an angle theta inside that circle. Well, we know that this theta is going to also correspond to a certain circumference around the circle. So in fact, we just convert this theta into the circumference, which, if you would agree with me that this circumference up here would be 180 degrees, and 180 degrees, well, that's 360 divided by 2. Let's also call this circle a circle of 1 unit of radius. So really, we get 180 degrees is equal to pi. And let's just put that back up there, as this is our central unit, the radian. Radians are going to be the main way that we're going to plot trigonometric functions, I believe. But if we want an angle theta for any circle, all we need to do is divide this r, divide this a by this r, the radius over the arc length. So really, theta is just arc length over radius. All right. Continuing on, we also know that, let's work some practice problems here. So we have 210 degrees, and we want to convert this into radians. So we are going to start by dividing it by 180 degrees and multiplying it by pi, as these are equivalent values shown up here. So let's see. I think I can pull out a 30 from that, and I'd get 7 pi over 6, I want to say. Yeah, that looks right. So let's say that that's going to be 7 pi over 6. Next, 36. Well, 36 times by 180 degrees over pi. And let's see, what can I pull out of that? I can pull out a 2. I can pull out another 2. I think that would give me 45. So that'd be 9 pi over 45. And then that can further be simplified to pi over 5, I want to say. There we go. Got it back. Let's see. And then for this 900, so I'm going to erase some stuff first, just so I can have some more space. Sorry, I don't have very clean transitions here, but 900 degrees times by 180 over pi. Well, I'm just going to call this 90 over 18 pi, and then I can pull out a 9 from that. So that'd give me 9 over 2. Or, sorry. If I pulled out a 9, that'd give me 10. So 5 pi. Right. 180 times by 5 is 900. 36 times by 5. 36 times by 5 is 180. And 210 times by 6 and then divided by 7 is 180. Yep. No. Yeah, I did do that right. Okay, cool. Okay, moving on. So trig functions. So our theta is going to be down here, and we have this right triangle defined. Let's make sure that we know that this is right. No, I don't want a square, my good sir. So if we're looking at sine, I'm pretty sure we all heard SOHCAHTOA in the past, so it's going to be opposite over hypotenuse. Then we have cosine, which is adjacent over hypotenuse. And then we have tangent, which is opposite over adjacent. Opposite over adjacent. Adjacent. There we go. Most people, however, have never seen these functions. The cotangent, the cosecant, and the secant. This one up here is the cosecant. Where is the secant? This is the cosecant. Sorry, I'm very confusing. And really, these are just our original functions to the -1 power. There it's reciprocal. So cotangent is the reciprocal of tangent, so it's just adjacent over opposite. Secant is going to be the reciprocal to cosine, and it's going to be hypotenuse over adjacent. And then cosecant is going to be hypotenuse over opposite. Now that we got our refresher of geometry, how do we expand this to negative numbers? It's a very useful thing for us to be able to use these inside of the xy coordinate plane. So let's just define a new hypotenuse here. And we are going to just, define some things here. So, let's see. Let's define this length as the square root of x squared plus y squared. So, in reality, our trig functions here are going to be as follows, I think. Give me a moment. Yeah. So, in most cases, most people would define this to be r, but I'm going to fully just go full out and give you in terms of x's and y's. So sine, as we know, is going to be our opposite, which in all cases is going to be our y's. So sine is always going to be our y over the square root of x squared plus y squared. Then cosine is going to be x over this x squared plus y squared. Tangent is going to be really neat and easy, and it's going to be y over x. Cosecant is going to be square root of x squared plus y squared all over y. Secant is going to be the square root of x squared plus y squared over x. And oh, I realized that I miswrote something, but that's fine. We're just going to call this one down here cotangent. And this is just x over y. Okay. And now we actually have a way to expand it to negative numbers. If we wanted to draw a graph, and we have a right triangle inscribed upon this graph, well, we can now have a theta such that we can have a negative value for this opposite and a negative value for this adjacent. Okay, continuing on, the unit circle. Now, the unit circle is actually going to be a wonderful tool for us, and you'll see why here in a moment. Let's say that this unit circle has a radius of 1, a 1 unit circle. And what if we inscribe a triangle into here? So we have this length, that is going to be our y. And we have this length here, that's going to be our x. And something really cool happens. Well, our sine value is just going to be our opposite over 1, which is just y. Cosine is really just going to be x. Tangent is y over x. Cosecant is x over y. I mean, no, I lied. Why did I do 2 cosecants again? I was really liking cosecant, apparently. X over y. That's why I was messed up. Okay. Secant is really just going to be 1 over x. And cosecant is going to be 1 over y. And now we have a way of having really nice values for our trig functions. And you'll find later on that this unit circle definition, let's remember that this circle is going to be x squared plus y squared is equal to 1. This is going to come in handy and be one of our trig identities. So one of the big things about trig is we need to know exact values of trig functions. So for this, I am going to make my pen a small bit smaller, and we're going to start work here. So we have all values that a trig function can take for sine and cosine. And you'll find that this is really all you need for the rest of trig, because all the other trig values are going to be based on it. So to start out, sine at pi over 6 is just 1/2. Pi over 4, it will be the square root of 2 over 2. Alrighty, sine of pi over 3 is going to be the square root of 3 over 3. And whenever we reach the peak of the unit circle, which I wish I had one drawn down here, but I don't. But that is going to be right here because we're halfway through pi. Continuing on, we have 2 pi over 3. So that's going to just be the same thing as square root of 3 over 3, or I lied. It's square root of 2 over 2. I don't know why I said square root of 3. Square root of 2. And it's also square root of 2 over here. I am sorry. Continuing on, we have square root of 2 over 2. Square root of 1 over 2, which is just 1/2. And then we have 0. Continuing on, we have negative 1/2. Negative square root of 2 over 2. Negative square root of 3 over 2. Negative 1. Negative square root of 3 over 2. Negative square root of 2 over 2. Negative 1/2 and negative 1. These values I'd highly recommend you memorize. And one of the ways that I think has worked best for me to memorize it is like inscribing the points on the unit circle. We'll go over how you might want to remember that yourself in a moment, but let's work on the cosine values. And what you'll find is they're in fact very similar to our sine values. Well, cosine at 0 degrees is really just going to be way over here. So this is its x value, and since this is a circle of radius 1, it is still 1. So it starts out at 1. Oh wait, never mind, there's no 0, so that does not start out at 1. It's going to start out a bit less than 1. It's going to start at square root of 3 over 2. Then at pi over 4, square root of 2 over 2. Pi over 3, 1/2. 0. And now, the x value of the unit circle is now going to start becoming negative over here. So it's going to start having negative values for the cosine. So it's going to be negative 1/2. Negative square root of 2 over 2. Negative square root of 3 over 3. Over 2. How many times have I done that? It's over 2. 0. Or not a 0. 1. Negative 1 to be precise. Negative square root of 3 over 2. Okay, negative square root of 2 over 2. Negative 1/2 and 0. Then we have 1/2. Square root of 2 over 2. Square root of 2 over 2. Then square root of 3 over 2. And then this is supposed to be 0. And this is supposed to be 1. This is what I get for not planning this out. I make mistakes, but we're all human. We do. So this is our complete value for all the trig. So if you ever want to know what tangent is, tangent at a certain point, tangent of, let's say, 5 pi over 6, well, you just are going to take the sine of pi over 6, which is 5 pi over 6, which is 1/2, over the cosine of 5 pi over 6, which is negative square root of 3, over 2, dividing by a fraction is the same thing by multiplying by its reciprocal. So we get 1/2 times by 2 over the square root of 3. Keep that negative in. So we get our final answer to be negative 1 over the square root of 3. Let me tell you this. Most calculus classes will not require you to simplify this. But if they do, all you need to do is multiply the top and the bottom by the square root of 3, because this is just the same thing as multiplying by 1. And now you will no longer have a radical in the denominator. And that would be your answer. That's no bad. No camera for you. I hate when it does that, but it happens. All right. So, I want us to find the area of this triangle in terms of A, B, C, and theta. Will we need to use all those letters? Well, let's find out. Well, earlier I said sine of theta is equal to the hypotenuse, or it's equal to the opposite, which in this case is going to be h over our adjacent, or not adjacent, but our hypotenuse, which in case is going to be our b. So sine of theta times by b is equal to our h. Well, h is our height of our triangle, and we know a is our base. So using our what we know for triangles of the area, it's 1/2 base times by height. So that would be 1/2. The base is a, so I'm just going to say a, times by b sine of theta, and that's just equal to a. That's a really nice exercise. All right. Trig identities. Well, there's a lot of them, and they will come in handy. Sometimes it's a lot easier to work through a integral if you can divide it up to smaller parts. And that's what these trig identities do. So to start out, let's start out with the most important trig identities. So as we know, we have a triangle, and it's on this unit circle, right? So let's see. So the value y we already know is sine of theta. And this value x is equal to cosine of theta. And we know our equation of our unit circle is x squared plus y squared is equal to 1. So we actually do have a way of knowing, of getting this basic trig identity. Well, x, well, that's just cosine squared of x. Y, that's just sine squared of y is equal to, or if theta. Theta. I am tired, but yeah, of theta. And this is our first trig identity. Now, there's a lot more that come from this. So let's look at it. And let's actually get back my normal size, because I like writing in big pink. There we go. So another thing we can do with this is we can divide this by either cosine or sine to get two other identities. So let's say we want to divide this. So we want to do sine squared of theta plus cosine squared of theta is equal to 1, and we want to divide this by sine squared of theta. Well, let's get started with this. Well, sine squared divided by sine squared, that's just 1. Well, let's see, what's cosine divided by sine? What is cosine divided by sine? Well, cosine divided by sine is just going to be cotangent squared of theta. And we already know 1 divided by sine is going to be cosecant. So that's just going to be cosecant squared of theta. All right, continuing on. So, let's see. What if we took sine squared of theta plus cosine squared of theta is equal to 1 and divided it by cosine squared of theta? Well, we would get tangent squared of theta plus 1 is equal to secant squared of theta. And these three trig identities come up relatively often. In fact, they are some of the more important ones. So I'd recommend you keep them in mind. But let's erase that. I'm actually going to... No, I'm not going to move them. But let's think for a moment. So, in my previous lesson, I was talking about the functions being either even or odd. And this has actually come up here too. That is wrong. That should be negative. There we go. So, sine in itself is a odd function. No matter what value of sine you input, like let's say you input negative pi, it's going to be the same thing as minus sine of pi, if you get what I'm saying. So like sine of negative pi is equal to the same thing as sine of pi, or negative sine of pi. So for example, this here would be, well, you'd go back around, so that would be 0, and that would be 0. That makes that easy. Continuing on. Cosine, on the other hand, is even. So no matter what value you put in, let's say you put in negative 300 pi, for whatever reason, that would be the same thing as inputting cosine of 300 pi. Let's see. And that's just some really unique properties of the trig functions. The next trig identity that I think I'd like us to go over is going to be these addition formulas. So let's say you, inside of this sine, you have two different components that are being added together. Well, the way that we can find this is by doing sine of x plus the cosine of, or times by the cosine of y, plus the cosine of x sine of y. Well, now if we want to do the same thing for cosine, it's actually going to have a different formula. For cosine, it's going to look like cosine of x cosine of y plus sine of x sine of y. All right. Okay, so now for the subtraction bit. So there's also subtraction formulas, and they are going to look mildly similar to the previous formulas. So we are going to have sine, for the sine, sine of x cosine of y minus cosine of x sine of y. So honestly, like identical, it's just subtracting instead of adding. And then now for cosine of x minus y, we would get cosine of x cosine of y minus sine of x sine of y. Again, they are identical other than the addition. Addition is for addition, subtraction is for subtraction. Well, tangents are very messy. They really wanted to just ruin it all. But yeah, you can't always have nice things, can ya? So, for the addition formula for tangent is going to be tangent of x plus tangent of y all over 1 minus tan of x tan of y. That's like a mess. But at least it looks almost identical to the subtraction formula as well. So we have tangent of x minus, instead of plus, tangent of y minus 1 minus tan x tan y. And here we have it. We have all the addition subtraction formulas for the trig functions. You might notice that we have excluded cosecant, secant, and all that stuff. And the reason for that is cosecant, secant, and cotangent all can be represented with sine, cosine, or tangent. As such, it's not necessary for us to have individual laws for them. In fact, it would make things a lot more complicated and harder for you to memorize. Most teachers that I know have not required me to memorize any of these formulas. I think they are just good to have on your noggin, you know? Plus, it just really serves as a benefit to you, especially being able to break down things like this in such a manner. Alright, let's continue on. So sine of 2x. Well, these are going to be our double angle formulas. They're going to be a small bit different. So sine of 2x can be, interestingly enough, composed as 2 sine of x cosine of x. And cosine of 2x can be composed as cosine squared of x minus sine squared of x. All right. Pressing forward, we have the double angle formulas for the cosines, and well, more or less just 2 additional ones. Cosine's kind of special, but we can also represent it as 2 cosine squared of x minus 1. We can also represent it as 1 minus sine squared, minus 2 sine squared, apologies, of x. And these are just all of the formulas. Well, interestingly enough, using these properties, we can now also discover our half angle formulas. So these are really useful for integral calculus, where we can break things up into less trig or chain rule type things. And sorry, a lot of this stuff's going to sound very unfamiliar because we haven't reached that point yet. But for some of you that are using this as a review, it might be very familiar. So cosine squared is going to be 1 plus cosine of 2x all over 2. And sine squared is going to be 1 minus cosines of 2x all over 2. Oh, geez, we're almost done, my good sirs and ladies. I appreciate all of you that have stuck in this far. This is definitely a doozy even for me. I think this is going to probably be the longest video I ever make. Alright, continuing on. We have the product identities. Sometimes it's useful to break things down into not being products. So the way that we're going to do this is sine times cosine of y is going to be equal to 1/2 sine of x plus y, and I'm going to draw a bigger bracket because there's a lot of stuff here, plus sine of x minus y. Close bracket, close big bracket. The next one, we have cosine times cosine. It's going to be 1/2 cosine of x plus y plus cosine of x minus y. Yep. And now, if we have a sine times a sine, it's going to be equal to 1/2 big bracket cosine of x minus y minus cosine of x plus y. And behold, these, my friends, are the trig identities. Yeah, that's a lot. That's a lot to take in. So, I wanted to work through a few practice problems here. So, let's first start out by expanding this. So we want to show that sines of x plus cosine of x squared is equal to 1 plus sines of x. Now, let me think of how I want to do this. So, let's start out. We are going to get a sine squared of x plus sine of x cosine of x plus cosine squared of x is equal to 1 plus 2 sine of x. Where do I want to go with this? Well, we know from one of our trig identities that the sine of x and cosine of x are going to be equal to 1. So let's just bring that out front. And we have some sort of product here. How would I like to do this? Well, we are going to have a 1/2, or we're going to just call this over 2. Let's make that eraser a bit smaller since I'm working in delicate spaces. So we are going to use our sine cosine. Undo, please. Undo. Sine cosine of y trig identity here. So it's going to be, cosine of, sine of 2x. And then we are also going to be plus sine of 0, or x minus x is 0, all over 2. And that is equal to 1 plus 2 sine squared of x. Where do I want to go from here? Well, sine of 0 is really just 0. But now I have a very annoying sine squared, or sine of 2x. So the way that we're going to break this down is we are going to break this down using this formula here. So we are going to get 2 sine x cosine of x. Okay, now we have to break this apart again. So let's see. That's my first time doing this, so this is definitely challenging me here. So we are going to get a sine times a cosine, which is the same trig identity we had earlier. I hope this is not about to be coming in this loop. So we have 1/2. So we now have a 1/2, and that was just x, so it's going to be sine of x plus y, which is going to be 2x plus sine of 2y, sine of 2y, or 0, sorry. And that's just going to be 0, so I'm not even going to worry about writing that down. But last time I had that didn't work out well. So, can I break this down another way? Can I break this down further, even? I don't think I can. This is actually a really good challenge. I will give it that. Let's see. Well, in the name of not wasting your time, I'm going to say that this will be fine for right now. Let's move on. So we have 2 laws in trig. And their names are going to be the law of sines and the law of cosines. Well, the law of sines states that in any triangle ABC, which I've drawn out, and it can be any triangle, no matter how wonky, the sine of A over A is equal to the sine of B over B, which is equal to the sine of C over C. Now, these laws, this law specifically is very useful for triangles where you'd know, let's say, sine of A and A, or perhaps you might know sine of B, B and A, or stuff like that. That is when it will prove useful, especially for finding those sine lengths. The law of cosines, on the other hand, is very different. In fact, there's 3 laws of cosines. And it's going to follow the same exact triangle, which I'm actually going to move off to the side. So it states that in any triangle ABC, if we have a side length A squared, it's going to be equal to B squared plus C squared minus 2BC cosine of A but that's not it. I said there was 3 of them. That looks like 1. Well, there are. But they all take the same form. B squared is going to be equal to A squared plus C squared. Okay, minus 2 AC cosine of B. And our third one is C squared is equal to A squared plus B squared minus 2AB cosine of C. So the pattern really is that for a corresponding side length A to the angle A, it's going to be it squared. You see, whatever side length is going to be equal to whatever cosine. That's the way that I like to remember it. Side length A goes with angle A. Side length B goes with angle B. Side length C is going to be with angle C. And that is the law of cosines. So, this law of cosines is used in a lot of ways. I think in general, trig is like one of the most applicable forms of mathematics. But I have a little problem for us here. Most people think of an area of a triangle in the form A is equal to, let's see, A would be equal to 1/2 base times by height. Now, is there an easier way for us to calculate formula? Because in this triangle, we don't have a direct way of measuring height. We don't have an angle theta. Like, I mean, we can pop out a law of cosines, find this theta, and then find this height. But let's see if there's an easier way. And in fact, Heron's formula gives us a way of doing that. So it states that for any triangle, ABC, we can find the area in a different way than 1/2 base times height. And this way is area is equal to the square root of S times by S minus A times by S minus B times by S minus C. Now you might be wondering, what's this variable S? Well, S, as I have pointed out up there, is going to be A plus B plus C over 2. Or it's the semi-perimeter of the circle. I mean, not the circle, the triangle. Whenever you say like semi, you like to think of semicircles in my personal mind. Well, let's work a problem, and I actually have one listed out right here for us. So we have, let's call this side length A, this side length B, and this side length C. So S is going to be equal to 4 times by 5 times by 7 all over 2. That's really just 70, if my math's right. So now what we're going to do is area is going to be equal to the square root of 70 times by S minus A. Well, that's going to be 70 minus A, which is 4. Then we have 70 minus 5. And then we have 70 minus 7. Now, I'm not going to ask you to calculate this without a calculator, so if you want to, you can pull out your calculator now. And it's going to look like the square root of 70 times by 70 minus 4 times by 70 minus 5, 70 minus 7. And now, if your math was right, which it doesn't seem right to me, something doesn't seem right. Or perhaps it is, but no, that looks way too big. That's all in a square. Give me one moment and I'll be back. So looking back at it, for whatever reason, I decided to do times instead of plus. Someone's going to point that out in the comments, but that's fine. You know, constructive criticism is great, and it's going to help me become a better teacher. 8 is going to be our actual side length, so let's replace that 8 instead of the 70. Oh, geez, I'd hope this triangle was not... I did not have that much area, because that would not be nice. Which, I'm just going to erase this last bit, because that's equal to 1. Okay, so in reality, it's going to be the square root of 8 times by 8 minus 4 times by 8 minus 5. And I get an area that I think is a lot more reasonable of 9.798. Alright, let's move on. And we are nearing our end here of this episode. An hour of trig. Trust me, I didn't like this either. It was serving as a reminder of why I didn't do this. This is also, there's probably going to be a very soon upcoming video about the inverse trig, but I will decide whether or not to make that. The inverse trig is surprisingly nice. So, I've made a table earlier of values, but now we get to graph this. Now, all of these functions are periodic and endlessly repeating. So, the 4 pi is the same thing as 2 pi, is the same thing as 6 pi, is the same thing as 10 pi. The only thing that's going to change is the x. The y is not going to change for those different values of pi, if you get what I'm saying. So, sine starts out at 0. Or, you know what? Let's actually zoom in on the graph. So pi starts at 0. At pi over 2, it becomes 1. At pi, it's back down to 0. 3 pi over 2, negative 1. 2 pi, 0. Negative pi over 2, it's going to be at negative 1. Pi, 0. Negative 3 pi over 2, that's the same thing as pi over 2, so it's going to be up here. Now, let's just draw our little graph. Connecting our trig, or our points on the graph with a nice little squiggly line. Brings you back to kindergarten. And this is our graph of sine, endlessly repeating. Now let's look at cosine, the other major trig function. The ones that all other trig functions are derived from. Well, cosine starts out at the value of 1. Then at pi over 2, it is 0. At pi, it's negative 1. 3 pi over 2, it's 0 again. And at pi, it is 2 pi, it's at 1. Well, negative pi over 2, once again, 0. And you'll see there's this symmetry. That's way too low. There we go. There is some symmetry in the y-axis. Let's just slowly draw out this sinoidal curve. little language trivia for you. What are sines and cosines, both called sinusoidal curves? Well, my good friends, this is the cosine, and you'll see that as you reflect it over the y-axis, it's the same. And whenever you reflect the sine over the y-axis, it's just the same thing as the negative. The cosine's even and the sine is odd. Let's look at tangent now. Tangent is really cool, I think, in my personal opinion. So, tangent is going to look like, well, from right here, you're not really going to understand it, but it's going to look like this. But I think there's more to it, and there is. These little dotted lines are asymptotes. And what you'll see is there's this infinite swirl of what almost looks to be like a cubic function going about. Cotangent actually has the exact same shape. However, it's actually going to be like flipped around. So at pi, cotangent is going to go swirling downward. Nope, no pictures. No, y'all don't get pictures of me. No pictures. It's going to go swirling down. And it's going to go swirling down again. And what you'll notice is these are endlessly repeating. All of these are. Cosecant is going to be a small bit strange, in my personal opinion. Or at least most people think. So let's draw out all of the values of sine on this graph. Well, for sine at pi, at 0, sine is 0. So let's just mark that point. Then at pi over 2, sine is, well, up here, and then it's once again 0. And we now have all the values of sine. Well, the definition of cosecant, and I haven't gone over this up until this point, is 1 over sine of theta. It is its reciprocal. So, this function can't be equal to 0. So let's put little asymptotes at where it's going to be equal to 0. And we know that if you're dividing by something that's smaller than 0, which most of the values of trig are, it's going to get really big. So let's find a value 1. Well, 1 over 1 is 1, so that's going to be our shared point for both. So what this is going to do is it's going to make like a very downward U shape. And there's another U shape. And this right here is what cosecant does. It's going to make endless amounts of U shapes. Continuing on to secant. Secant is 1 over cosine squared. 1 over cosine, not cosine squared. So cosine at 1 is going to be 1, or 0 is 1. Pi over 2, 0. Pi, negative 1. And here we're not going to get a very good example, but it's going to work. Trust me, it's going to work. So, let's see. Let's once again find where it's 0. Well, it's going to have an asymptote here then, and it's going to have an asymptote here then. Well, since this is positive and the denominator is positive, this is going to go skyrocketing into the sky. And down here, it's going to go skyrocketing into the ground. And same thing down here. And you'll notice that these graphs also look the same. And that is the beauty of trig. They might not be able to be represented by like tan or by algebraic ways, but they can be represented transcendentally. These functions are absolutely amazing. They have such great real-world applications. And this is where I'm going to leave you off for today. I want to thank you all for joining me. I hope you have a wonderful rest of your days. Please enjoy, and I hope you found it informative. Have a great rest of your day.